getting there. I'm trying to get the PowerPoint up. Nice.
Yeah, no, I don't really use one that does not install. You cannot do data recovery. That's completely a myth for any modern hard drive. It's 2000 pretty much. It's not really possible. Those secrets that they say the secret machine can read everything, it's a lie.
All right, we ready?
So Brian's going to give a talk about Docsis now. So please welcome Brian, and here you go.
How's it going, guys? All right, so my name is Brian Wilson. I handle is Slim Jim 100. I actually work for this company, but I'm here on my own recognizance. So the group I'm with is Middle Georgia Computer Users Group. We're actually in the process of opening a hackerspace here shortly in Macon. Is it not getting it? All right, can you hear me? Yeah. Okay. So I'm part of Middle Georgia Computer Users Group. We're out of Middle Georgia. Probably the best thing to say is the Macon area, about 80 miles south of here. Here shortly we're going to be, we're working right now on opening up a hackerspace. So the web address for that is tech-node.org. Thank you. And like I said, we got a LAN party we're going to be hosting April 2nd and 3rd in Macon. So you can go to the website and go there and check out the information on that. So today I want to just go over some of the basics of what Docsis protocol is and how it interacts with the CMTS. So how many of you here have a cable modem at home? Just about everybody. All right, so a few of you probably have DSL, and maybe some of you have fiber to the home. Hopefully nobody's in dial-up. So Docsis is the protocol your cable modem uses to communicate over the radio frequency to get back to the cable company's head in for them to provide the ISP services for you. It's very, high-level look at it. So what we're looking at now is we're looking at the cable broadband architecture, and we're going to look at it in a few different ways. And there's going to be simpler ways, and then we get a little more advanced in looking at it. But as you can see on the slides there, you've got the internet cloud over here. Then you have the service provider IP core network. Within that network, that connects then to the CMTS, cable modem transmission system, which is a big router. And then from there, it actually goes out over the optical plant, eventually to coaxial RF plant. And if we're really lucky, we'll get it to a drop, and then we'll take it into your house. From there, it'll plug into your modem, set-top box, EMTA, whatever services you subscribe to. We're focusing on the cable modem here today, and we're going to go over how Docsis works and how it interacts with the CMTS and kind of go over the very basics. Has anybody heard of Docsis before now? Okay. Yeah, if anybody has a question at any point in time, just... No. He asked if I was going to talk about cable modem and capping, uncapping, hacking, or anything else like that. No, I won't talk about that because that's pretty much theft of service. So it's illegal.
If we get you drunk, will you talk about it?
Probably not. I could probably tell you that anything you do in a Docsis network, because it's an RF signature, can be tracked. So as anonymous as you think you might be, with the RF spectrum and information, timing offset, the actual decibel level of your device, I could probably track you down within 50 feet on the cable plant of where you're at. So even if you were to clone somebody else's information and show up somewhere else in town and masquerade as them doing bad things, we could still find out exactly where you're at. And it's instantaneous. We just have to do some basic formulas to figure out timing offset from fiber optic to coaxial, and then where the tap loss is. And I can usually get within about 50 feet of where you're at. And if that's in a building, yeah.
Brian, I'm going to guess you work for Cisco.
Yes, I do.
Did you activate Cisco gear?
Yes.
Can you just, like, 10 seconds tell us what you do?
Okay. So for Cisco systems, I'm a network consulting engineer. Title pretty much says it all. I support major cable ISPs. My side is a consultant is I don't even necessarily have to recommend Cisco gear. When the customer engages my team, we are advocates of the customer. So we are their consultant, though we do work for a vendor. Our job is to make sure their life gets easier and they have the right solutions in their network, not necessarily buying this or that, but is this what you need and how is it best implemented in your network to help you make money? So what is Docsis? Docsis is data over cable service interface specification. It was created by Cable Labs. Cable Labs is a nonprofit research and design custodian dedicated to pursuing new cable technologies. Cable Labs was created by the cable companies. They didn't want proprietary expensive gear that they couldn't get out of. So they pulled together the big guys, and they basically formed Cable Labs, a nonprofit organization. And then the vendors have to, if they want to be Docsis compliant, they have to go in and work with Cable Labs to get their equipment certified. Once their equipment and their technology is certified, any member or vendor that is also in that the Cable Labs group has access to that information patent-free. So that keeps costs down and actually allows you to have a $40 modem, which when you look at the chipset, the information, all the actual hardware that's in there, if it was proprietary, it probably would have cost about $700-800. So with having Cable Labs, it keeps costs down and it keeps things open. And it is an open standard with what they write. A lot of the stuff they'll probably want you to become a member or sign into to get some of the information. But if you're really interested in Docsis and you want to know all the information about it, bit level, the information is available out there. So Docsis defines the interface requirements for cable modems involved in high-speed data distribution over cable television system networks. Basically, it makes your cable modem work. So a second ago, we looked at the cable TV plant. Well, now we're going to take another look at it. And this time, we're looking at it in a little bigger view. So, there, okay, my mouse shows up. All right. So here you would see like the antenna would represent off-air video transmissions, local TV channels. Sometimes your cable company may not have a direct fiber feed to get the video stream in, so they may actually put up a set of bunny ears on a little tower out there and actually pull the signal in that way to inject it into the channel lineup. They're also going to be pulling out services off of large-scale satellites, and those are going to be services, your HBO, ESPN, CN, all the services they offer you. They're not locally made; they're from all over the place. They're other broadcasters, and they're going to collect those off the satellite. Once they get those, they're going to bring them in through fiber, and eventually go into what's called a head-in. The local head-in is where all the equipment is. That's where the channel lineup's at. That's where you do all your combining. That's where your transmitters, your optical transmitters are. Because for the cable company to provide services to you in the modern day environment, they actually send all the information down fiber all the way up into your neighborhood into what's called a node. The node transfers the optical signal back into an RF technology. And that's usually between 5 and 1 megahertz or gigahertz. So within this diagram here where you see the local head-in, you see the symbol for a router. You've got receivers, modulators, scramblers, HFC interface, which is hybrid coaxial fiber. You've got the local head-in, and then from there you go to downstream and upstream. In this case, they're doing actual, these are going to be separate optical fiber paths. Once you get from the optical fiber paths, you eventually get to the dark blue line here, and that would be the hard line coax that's hanging on the telephone pole. Not the skinny stuff in your house, but the much more robust aluminum fed. Eventually that gets broken down through amps and line extenders. It gets stuck to the side of your house at the audit box, and then from there it goes in the RG59 cable you know of that you have in your walls now. Yet again, another demonstration of the same basic diagram in a different format. And what we're trying to pretty much represent here is, you see the head-in, you also have what's called hub sites. So that's going to be another site similar to the head-in that may be closer geographically to where the customers are going to be serviced. And then the signals may actually leave there optically before going to coax. And then these little things here, node, these are actually fiber strand about the size of a shoebox. They're pole mounted or they're in pedestals in the ground. And, that's where you get that. And then also in the outside cable plant, you're going to have power supplies every so often. So it's just going to be a big box hanging up on the telephone pole or in a pedestal on the ground. And then with inside those, there's car batteries, and they get local power from the power company, but they have battery backup in the event local power is lost. So even when the power goes out, 9 times out of 10, your cable TV is not down. You just can't turn your TV on. So if you have EMTA voice services to your cable provider, so if you have a voice-enabled cable modem, a lot of those will have a battery backup in it. Reason being is just because the power went out, it doesn't mean the cable TV network's down. You can still make phone calls. Most models of the EMTA devices will shut off the Ethernet port. So even though you got a backup, you get your laptop running, and the reason they do that is the battery can only sustain the device for so long, and keeping the Ethernet port and the RJ11 ports hot at the same time would drain batteries unnecessarily. The idea behind the battery backup is to keep the phone service up in the event you have an emergency or that your alarm system still needs to call out. Go ahead.
I've noticed that when there is a power outage, even though all of my computers and networking equipment is on UPS and it's still working, that my internet connection, which is over cable modem, is down. Is that a flaw with the battery backup and not my own, or?
It could be, or it could be the simple fact that there could be signal loss or an active component failure. So when you have the power loss, it actually could be, catastrophic. So, yeah, and the amplifier goes down. You 9 times out of 10 you're going to lose it because you're going to take a large dB attenuation there. The only other thing to point out here real quick would be there's this little arrow here that says downstream. This is the frequency base you're actually going to receive from the cable company directly to your house, 88 to 880 megahertz, or actually it could even go up to 1 gigahertz. So that is also referred to from the RF guys as the forward path. That is the RF frequency coming from the cable provider to you. Well, that'd be kind of useless to have one-way communications. I mean, if all you could ever do is listen and you can never respond, well, then you really don't have communications. It's more like a radio talk show. So to provide services like pay-per-view, video on demand, data, voice, stuff like that, you got to have a path coming back. The early days, they actually did telco return, where you actually still had to have a telephone line. And basically what it was is you received your download over the cable modem, and then your upstream traffic back was actually over an analog modem, which is called telco return, where it actually dialed a modem back to get the upstream back. Typically, people are like, why isn't it symmetrical? Why is the service not symmetrical? Well, I've just pointed out the downstream. There's another little area over here you see where it says upstream. That's only 5 to 42 megahertz. You see there's a big difference in the frequency base between the downstream and upstream. What that being is the upstream is extremely limited. Now, there's not a lot of devices that need to talk back. So you have your cable modems. You may have proprietary phone systems devices. You may have the set-top boxes that need to transmit back pay-per-view information or channel lineup information. It's really cool that you can call your cable company and change your service, and the box magically gives you those channels. I mean, nobody likes to wait for somebody to come to your house to fix a service or add something. So with the two-way communications, it's not just convenient for the cable company themselves, but it's also convenient for the customers. All right, I'm pretty sure most of you can read, so I'm not going to bore you with reading. But your cable is going to come over. Your cable TV service is coming over a 75 ohm coaxial cable, usually RJ59, sometimes RJ11. 6. Again, kind of how I explained it. Back in the old days, when cable TV was considered community antenna, it was one unidirectional, one-way data path. They provided you pictures. They sent the information to you. You never talk back. More recent networks now is the HFC design, where it's actually fiber up to close to the neighborhood, and at that point, you have 2 optical paths, one forward and one return, where you can actually transmit data back. And your forward is considered your downstream, and your return is considered your upstream. So you're combining. So what you have here is, in North America, we use what's called Annex B. Okay, there's actually 2 annexes. There's an Annex A and an Annex B for your frequency allocation. So with Annex B in North America, it's actually a 6 megahertz block is considered a channel. In Europe and Annex A countries, it's 8 megahertz. So it's a slightly larger, and it's the same thing with Euro and everything else with the T1 versus E1. They always wanted it a little bit better. So good for them. But most of the equipment out there is going to be suited for Docsis. There is 2 flavors of Docsis, Docsis and Euro Docsis. And there is one little additional Docsis out there called J-Docsis for Japan. The only difference between Docsis and J-Docsis is they actually give you the ability to have a slightly larger upstream frequency base. So in North America, we have 5 to 42 megahertz. In Japan, it's 5 to 65. And then in Europe, it's also 5 to 65. But the JDOCSIS doesn't use Annex A. They use Annex B, 6 megahertz on their downstream channels. So if you have that frequency base, that 88 to 880, if you're actually inserting media or MPEG frames in there, and you were doing it in 6 megahertz blocks, you got to make sure you only put one service there, video, whatever it is, right? Either one TV channel, one HD channel, one Docsis carrier, depending on what you're injecting. But you can't inject 2 carriers in the same exact frequency on, at the same channel width, because you're just going to get garbage. They're going to basically ride on top of each other, and it's going to be noise. So you do have to make sure you properly place and map out your channel lineup. And then on top of that, wherever you have, a good 6 megahertz space in there, you can allocate that to a Docsis carrier. The Cisco 7246 or 7200 series UBR, Universal Broadband Router, or Uber, is the one of the product family lines that Cisco uses. Motorola uses a device called a BSR. Outerz0ne uses one called a C4 or a C3. And then ADC Big Man used to have a device called a CUDA, but they went under and stopped making it. And then Terion had one too called a Blue Wave, and they went under and Motorola bought them. So in the CMTS market, for vendors that actually can sell the equipment to make the cable modems work, you really only have like 3 vendors to go with: Motorola, Cisco, and Outerz0ne. Cisco has the largest market share. There's pros and cons with each vendor's hardware. Upstairs in our room in 226, I actually have a 7246 VXR router up there with a 6-foot cable plant built out with cable modems actively online. After this talk and later this evening, probably after 6-ish, if you want to come up to 226, just knock on the door, and if you actually want to come in and jump on the CLI, we've got $300,000 in equipment sitting up there you can play with. Go ahead. We're probably going to have the security thing with the door just pried open. But you can find myself, Brian. You can find DJ. You can't miss Jason. He's a little guy. You've got Bliss and Troy back there sitting side by side. So any of these guys here are part of the Middle Georgia Computer Users Group. What's that? Well, the door is locked, and this device is not light. You can ask DJ, because his back's better than mine. I just don't see anybody really trying to get out of the building with that. Plus, it's all serial numbered and trackable, so.
Each one of those connections, is that one cable model?
No, and we're getting ready to go into that. And if you wanted to see it real time, like I said, we've actually set up a 6-foot plant up in the room. I was going to try to bring it down here, but then I talked to Scott, and Scott said, I'm going to have lots of stuff on the table, and it's going to take me probably 20 minutes to get it all up. And I was like, well, yeah, and I really don't want to carry that router down. So we got the router actually set up live and ready to go up in the room. I think we have like 7 or 8 modems on it. We could even add more. I only brought a 16-way splitter, so I only can actually allot so many devices plugged to it. So this device here, if it's the 7246 VXR, and I'm not trying to say anything, I don't really care. I don't think any of you could afford it or have a need to buy this equipment, so I'm just explaining the technology. This device here is not end of life. It has been around for like 12 years. But just recently, they've come out with a newer line card for this one and a newer processor, so it will be able to do Docsis 3.0. So some of you probably heard the terminology Docsis 3.0, and you're like, wow, that's going to be great. Well, each version of Docsis has to be backwards compatible through Cable Labs. So Docsis 1.0, there was no quality of service, best ever data, blah. Docsis 1.1 actually added QoS and the ability to peel out different kinds of service flows and do dynamic service flows. Docsis 2.0, the only thing that did was actually increase the modulation in types of statistical multiplexing you can do on the return plant or the upstream to allow higher data throughput on the upstream. It didn't change how fast you could download. That was the same as Docsis 1.1. And then Docsis 3.0, we've in essence basically given you the ability to bond multiple downstream frequency channels. So where you had one downstream in the past, we've actually allowed you to think of it as RAID to stripe that across. So where you had one downstream, now you could technically have like 8. And where you had one upstream, you could actually bond 4. And we're just basically using packet sequence numbers to recombine it back to you. There is some other things like IP version 6 and Docsis 3.0, advanced multicasting, 256 AES encryption built into the device to protect your data, stuff like that. But the biggest motivator for Docsis 3.0 is, one, defend off FiOS, fiber to the home. Two, provide faster speeds. With there's always politics behind everything, and with the new administration saying they're going to put money in getting broadband to everybody, which has been said before, it does give the MSOs or cable companies a little motivation to go out there and start upgrading some of this equipment. It is not cheap or easy to do this. It's not like flipping a switch or buying a new box. Because your older devices, they have to be backwards compatible. If you still have Docsis 1.0 devices on your plant, you can't turn on all the features for Docsis 3.0 without making those things brick. And the average cost to roll a truck to somebody's house is $100, because you got insurance, the employee, all kinds of stuff, the vehicle. So if you've got 30,000 devices on your network, a small network actually, that's a very small network, and 10,000 are Docsis 1.0 devices out there still, you're going to have to find a way to get those off the plant. And if they're leased to the customer, okay, it's your responsibility. You could probably roll a truck. But if the customer owns it, they may not want to upgrade. So unless you're giving them a modem free, so now you're not only are you paying $100 to roll the truck, you're actually spending another $100 in hardware, and they're paying $35 a month. So there are some roadblocks that aren't all technical. Some are technical, some are financial. And it isn't necessarily about the equipment. It's just about the fact that this stuff is backwards compatible for a good reason, but it can limit. So if it's a greenfield deployment and it's a brand new place and you're just lighting it up, you're good to go. Of course, if that's also the situation, you may go with WiMAX or something wireless, or you may just run fiber to everybody's house. So there's pros and cons to everything, and there's multiple technologies. And some customers I support actually own the telephone company. They actually have fiber all the way up to like the edge of the neighborhood, and they have a cable plant. And they're trying to figure out how they get most bang for their buck. And 9 times out of 10, they're going with Docsis. The simple fact is there's a lot of research there, and it's a very strong protocol. Well, Docsis is a protocol, so I don't really know what a competitor would be. No. There used to be very close standards, and there was no necessarily Docsis at the time. So the original cable one was like the old shark fin and some of the original stuff out there. That was proprietary. So not only did you have to buy this vendor's hardware, you had to buy this vendor's modem, which makes it very expensive. So this is going to go through, and again, I'm not going to read it verbatim for you, but this is representing what's called a 1x6 line card. 1 downstream, 6 upstreams. So remember, the downstream is from the cable company out to the customer. The upstream would be the return path. So on the downstream, I only have one port. Remember, I have an 88 to 880 or 1 gigahertz range on that downstream. That's 6 megahertz wide. And I'm suiting that down, and that's actually going just like one little neighborhood area. And that's the downstream. That's your download. Now, if you need to talk back to the CMTS, you're going to have to come over an upstream port. Excuse me. So on the upstream side, you can actually, it makes sense to have multiple upstreams supporting a single downstream. And since this is an older line card, I think this actual line card we're looking at right now is end of life. This slide deck's kind of old, but it covers some of the real good basic stuff. I didn't want to come in here with like Docsis 3.0 and talk about like MDD messaging, and you're like, huh? I want to try to keep it basic and keep you guys in the same note. We can go a lot deeper later, but basically, in most cases, you're going to have one downstream and possibly multiple upstreams. Now, the devices using the upstreams, it'll be multiple devices, but one device, one device may, if it's less than Docsis 3.0, cannot use multiple upstreams by itself. So one modem won't be talking on 2 upstream frequencies. Though there may be 2 upstream frequencies available to it, it'll pick one. And then as utilization and network connectivity pick up, it can load balance between them and move the guy over to this one or over to that one. And you can actually have multiple downstreams too and do load balancing across downstreams in the same fashion. One other thing to point out, the little device down below this, you see from the downstream, they got this here, and then they got an attenuator, and then they got this little device called upconverter. So originally the downstream, just like in the TV network when you got a channel off a satellite receiver, the output was what's called IF, intermediate frequency. That is at 44 megahertz center frequency, the end. Not modifiable, that's what IF is. So if everything came out at IF at 44 megahertz, well, I can't really do everything there. That's where you get the up converter, where it takes the IFN and then turns around, and in the up converter you program what downstream frequency or channel you want to provide that service on, and that helps you build your channel lineup. All of the newer cards that are for the different types of CMTSs out there with all different vendors now have built-in up converters, so you don't have to have a separate piece of equipment. The device I have upstairs in our room has 3 1x6 cards and a 2x8 card. The 2x8 card has a built-in up converter, so we have one less piece of equipment, so that's the one we're hooking the modems to right now. But just a little side note. So 44 megahertz is what is called intermediate frequency in the cable world. So our upstream, again, I was explaining earlier, our upstream range is from 5 to 42 megahertz. Typically, that's pretty low. That's pretty far below the lowest downstream TV frequency, which would be sitting about 88 megahertz. And kind of a sidebar real quick, as I was talking earlier about channel lineups. So 1/6 megahertz slot in the downstream for a TV channel, well, that's what you need for one analog TV channel. But if you're doing digital, I can actually fit 10 digital channels in that 6 megahertz block. If you're doing HD, I can probably put 3 HD channels in that 6 megahertz space. But if you're doing analog, it's extremely wasteful, and it takes that whole 6 megahertz carrier. That's another reason the FCC is pushing to get rid of analog TV, because from 88 to 500 megahertz is the analog range. And that's basically wasted bandwidth. So where I could have put only one carrier, one television carrier per 6 megahertz, if I can get rid of the requirement to carry the analog, I can now stack 10 digital channels and possibly 15, depending on compression, in each one of those slots. And then I can stack anywhere from 2 to 4 HD channels per 6 megahertz block. So again, analog is extremely wasteful. Cable modems. These are some older pictures of some modem devices, but basically, I think we all understand kind of what a cable modem is. They usually have 2 data interfaces, at least classically they did. They had a USB port and an Ethernet jack for the customer, and then an F connector, or coaxial input, for the cable company's feed. Any of your newer cable modem devices, you're probably not going to see the USB port on it anymore. One, I think it was limited to about 11 megabit per second actual throughput, and 2, nobody used it. It's just an expensive additional port you have to put in a piece of equipment that almost nobody uses. So most of the newer cable modems out there from all the vendors have taken off the USB port. So there's an Outerz, a Cisco, a Linksys, which is also Cisco, and a Motorola in the picture below. So cable modem upstream and downstream. I've kind of beaten this already, so I'm just going to touch it real quick. The downstream, 88 to 880 or possibly 1 gigahertz, very large pipe. Lots of places you could put Docsis carriers. The upstream, 5 to 42 megahertz, not a lot of places to do data. Not a lot of frequency base there or RF spectrum that we could use. That's another reason why you don't have symmetrical services. That's why you could get, a lot of times you have something like 10 down and like 1 up.
Do they plan on to increase the upstream?
Sure, Docsis 3 has increased the upstream to 65 megahertz. The only problem is the cable TV plant has stuff called roll-off filters and diplex filters, and those actually cut the signal off at about 42 megahertz. So for them to provide a bigger upstream, they got to go out and replace every active and passive device on the telephone poles.
And the whole thing is they just want to be able to broadcast more downstream and more content to people. Is that why there's a larger downstream frequency than upstream?
Not really. Remember, internet and data is something that's actually pretty modern. Cable TV's been around before the internet. Nobody was using that frequency base. It's actually a really bad place to try to shoot to actually probably do data communications. It's very noisy. Does anybody know the frequency of citizen band radio? 27 megahertz. That's right in the middle of that carrier. So if anywhere in your cable plant there's a loose fitting, a squirrel chewed on the hardline feeder, somebody got a cheap Radio Shack twist-on connector, something like that, you actually can take what's called ingress and injection or have suck out of the RF at 27 megahertz. So I can't put a Docsis carrier there now because there's too much noise there. It won't transmit right. There's also 6 meter, 5 meter ham that can interfere. Remote control little kids remote control RC cars, that's at 27 and 42 megahertz. So there's a lot of characteristics that people don't really think about, but your RF plant in the field is like a living creature. It's constantly changing. It's constantly affected. Your decibel levels in the morning and the evening are going to fluctuate, because what happens with metal when it gets hot? It expands. The distance between the two devices have now actually changed. So there's a lot more to it than just the extreme basics. And if you really want to get deeper on RF, like I said, sync up with me, but you could spend your whole career just trying to understand the characteristics of signal. So it's best just to get a good grasp where you have a good understanding of the basics of how it works, and then continue to build on, and not try to dwell too long in one area, because none of us can be like know-it-alls at everything. We can be good at something, and we can be okay at a lot of things, but there's no way, and there's a lot of stuff I don't know, and if I don't know it, I'm going to tell you I don't know. But I'll probably be able to look it up for you. So we're looking at the downstream. There's something else. So I've told you the channel was 6 megahertz. There's one thing I didn't tell you yet, and it's the modulation scheme. So how are we modulating the signal? Well, currently you have about two choices for modulation: 64 QAM or 256 QAM. So the raw throughput of a 64 QAM carrier that's 6 megahertz wide is about 27 megabits per second for data traffic. A 256 QAM carrier will give you about 38 megabits per second. The other two fields over here, where it's talking about required and minimum CNR, that's actually carrier to noise ratio. It's not the same thing as signal to noise ratio. They're actually two different measurements, but people mix them up. On the upstream side, and again, I'm not going to sit there and read verbatim every part of the slide, because I'll run out of time. This is normally like, I cut 150 slides out of this, so there's only 70 here, so it's not too bad. And we probably won't cover all that, but normally the basics class would take a week to go into with labs to kind of cover some of this. But on the upstream side, we actually have different channel widths we can use. So on the downstream, we're locked in at 6 megahertz, Annex A or B, because those are TV. That's what the TV industry did way back when, and the FCC gave them. That's how they were allotted how to give out spectrum. Well, on the upstream side, that's more recent. That's for like pay-per-view, for the internet stuff. So we're a little more flexible with that. Well, you actually have different channel widths you can select when you're configuring the router. You can do 200 kilohertz, 400 kilohertz, 800, 1.6 megahertz, 3.2 megahertz. Or if your plant is pure Docsis 2 or better, you can actually even do a 6.4 wide megahertz carrier on the upstream. And then down below, there again is also different kinds of modulation. You have QPSK, which is robust and can handle noise but doesn't provide a lot of throughput. You have 16 QAM, which Docsis 1.0, 1.1, 2.0, and 3.0 are all able to use. And 16 QAM is a little more susceptible to noise, but gives you more throughput. So if your maintenance guys out there in those bucket trucks aren't tightening it up and fixing that plant daily, you're going to have a harder time running 16 QAM without taking a higher bit error rate or modulation error rate, depending on where the failure is. You may only be able to do QPSK because it's much more robust. And basically, just think of it as error checking. If I take one error, I can assume what it was and fix it. But if I take 3 errors in a row, at that point, I probably can't fix that because I don't know how to correct that 1 or 0. That's the same basic theory here. When noise comes in, it overrides legitimate data and causes this scrambled, garbled crap, and you're unable to really correct it, do error correction on it. The throughput ratings here. So with QPSK, you got 200, 400, 800, and 1.6 and 3.2 wide channel widths. You're not going to see anything out there today that is smaller than 1.6. The average is a 3.2 wide carrier. If the company that's servicing you thought ahead and got rid of the 1.0 modems and 1.1 modems, and all the modems in their plan are 2.0, then they actually can do a higher upstream modulation and a bigger channel width. They can do the 6.4 wide, and they actually can do a 64 QAM upstream, which a 16 QAM gives you about 10.24 megabit per second up. A 64 QAM is somewhere around 24 megabit per second. And then there's also other ways to do that too. Again, you have your required CNR and your minimum CNR values. Any questions at this point? QAM is a modulation type. It's much beyond this talk, but yeah, I mean, we'd have to go into some deep math too to explain it. It's easier just to explain this than to try to go through the slides. But basically, through the picture, you can see that the red line would be a downstream, and then you see the other color lines, the blue, orange, and green. Those are upstreams. Remember I told you you can have one downstream, but you might have multiple upstreams. In this case, each one of these streets or service areas are sharing a downstream, which, as we just seen, has a lot more throughput than an upstream. But each service area may have a direct route back to that CMTS on its own upstream. So how's that work? Well, each of these upstreams can actually be set at the same frequency because they're not going to the same people. Just because they share a similar downstream doesn't mean that's at a different frequency. There's a diplex filter there. So you take the high frequency here and the low frequency there, and you combine them together and you feed the customer. There's no backfeed across the downstream or the upstream from the other carrier or connection. So that allows you to actually run the same frequency on your upstreams and run the upstreams to multiple service groups. You cannot put the same upstream, you can't use upstream 0 and upstream 1 to the same node in the field at the same frequency because, again, you're riding atop each other. They would be at different frequencies. So how does the cable modem come online? Anybody have any idea right now? Besides people that know me. You plug it in, and how does it know how to transfer data and actually communicate with the CMTS? Is it auto magic? So, at this point, if you're not bored to tears just yet, I'm going to actually explain the cable modem ranging process and how it comes online, because it is a systematic process, and when troubleshooting errors, I can pretty much figure out where the problem is by looking at how it ranged or if it was able to complete ranging, because it'll tell me. I mean, most of us here understand troubleshooting, right? We don't start at layer 7. We normally start at layer 1, right? Is it plugged in? And then, okay, is it plugged in? Okay, is it turned on? And that's the basic trouble. That's the basic theory here is when the cable modem first gets there, right, and you plug it in and you turn it on, well, what's it going to do? Well, it's going to scan for a downstream frequency. It's got to listen before it can talk. Well, everything's actually encoded in MPEG on the RF. But there's a special frame header on the MPEG frames for Docsis. Well, you could actually have multiple. You could have one cable company, but you could actually have them reselling their cable service plant with another CMTS from a competitor or another company on the same cable plant. So you got to make sure the modems go to the right place. Well, part of the ranging, the initial ranging process, the first thing it's going to do is it's going to start scanning frequencies on the downstream. And in this example, this is actually a debug session from a Cisco modem. We can see it's at 537. Didn't see nothing. So then it goes the next frequency. Why is the next frequency 6 megahertz up? Because it's the channel width. North America. It keeps going. Eventually, it'll actually see, and here it says, cable modem log DS downstream, 64 QAM lock acquired. It found a downstream 64 QAM signal, and it's like, sweet. I found my downstream. Now I got to wait. And the wait state at the very last line there where it says wait, UCD state. UCD stands for upstream channel descriptor. It knows, it can hear now, but it does not know how to communicate back to the CMTS. It doesn't know what frequency, what modulation scheme, what channel width. It doesn't understand that yet. That's why it's waiting for the upstream channel descriptor, because the CMTS and the downstream is always telling everybody, just in case somebody wants to come online, it's always screaming out the upstream requirements for that downstream. So if you're on this downstream, if you just came on this downstream, by the way, I have these associated upstreams at these set parameters if you want to talk to me. So it goes through the UCD. So now it's scanning through, and it actually finds an upstream channel descriptor. In this case, the upstream channel descriptor is telling it 33 megahertz is the center frequency of where you need to be to talk to me. On top of that, it's also going to negotiate other information like modulation, channel width, stuff like that. Okay, so ranging process. There is something that you also have to understand too, is the cable plant. So when it comes to you, it comes to your neighborhood on fiber. When it hits that node, it's either up on the pole or on the pedestal. the people that are closer to that node, this isn't DSL, they don't get to go faster, but their signal characteristics will be different than the guy further down. Remember before I told you plug something in my plant that isn't legitimate and you start trying to screw around, I can find you? Well, this is why. You can't come online without properly knowing the right timing, when to say, how to say it, and you have to have an offset. So I have to understand the furthest modem away. I have to explain, I have to have built-in delay on all transmissions just in case he's talking too. And the same fact, I can also figure out the distance in the plant through the timing offset. But there'll be different characteristics too. The guy that's closer won't have to transmit as loud. The guy further away down the plant, the far cable modem, he's actually going to have to speak a lot louder for me to hear him as the CMTS. So his transmit value in decibels is going to be a lot higher than the guy that's closer up. There are other ways to combat that. The actual taps they plug your drops into have decibel values, and they can change the plates to add more attenuation or less attenuation, depending on how far away you are from the HFC node. Typically, so an HFC node typically would provide services depending on the cable company and their migration plans. Because okay, the faster the speeds they sell you, the less customers per node you want, right? I've yet to actually meet a cable company that oversubscribes on purpose and wants to be at 90% bandwidth utilization per node. Most of the time, I've seen anywhere from a customer I recently worked with only had 32 customers per fiber node. The average is about 250 to 500, depending. 90% of your users are using no bandwidth. Almost never. They're checking their email and looking at Facebook. They're not downloading stuff, right? And that's the customers you like. They pay you the 50, 70 bucks a month, and they don't even really use the service. Then you got the people like us. We want the cheapest cost, and we're gonna BitTorrent that thing till it bleeds, and we're gonna take as much bandwidth as we can get out of it. We are the bad customers. So the theory goes, 5% of your 100%, like 90% of your bandwidth is actually being utilized by like the top 2% of your customers. Like it's only like 2% of your customers are using most of your bandwidth. Everybody else is really doing nothing. They're doing their Windows updates and like searching on Google. So, kind of back to the ranging process. So, this is debugging actually on a cable modem, and this is basically. This is a physical console into a cable modem. I'm actually looking at its process and the messages it does. I'm watching at each stage as it tries to come online and actually get an IP address and hit the internet. So the first stage was it scans the downstream and finds a frequency that is actually Docsis. Once it finds that downstream, it waits for an upstream channel descriptor. A second ago, we found that, 33 megahertz. Well, now, in the ranging process, we actually have to work on getting our power levels correct. So the first thing I do, and I say to the CMTS, can you hear me? And I wait for a response on the downstream. If I don't get a response, my assumption is I didn't speak loud enough. So then I do it again. Can you hear me? A little bit louder. And I keep screaming until finally I get a response. So in this debug here, you see that it starts at 6 dB, then it goes to 9, then 12, then 15, then 18, and then right there, range response message received. It got word back that the CMTS could hear it. At that point, the CMTS might say, dude, why are you screaming? Turn your level down 6 dB. Or, I can barely hear you. Can you talk a little louder? But that's the ranging process. That's ranging state, which is called init R1. And that's just, they finally actually had communications. Guess what? Physical layer works. I screamed, can you hear me? And the CMTS came back and said, I can hear you. By the way, don't yell at me. So, the next part of it is actually more or less the fine-tuning part where he says, hey, yeah, I hear you. You're too loud. You're too quiet. Do a power adjustment for me. After that's done, the last stage is ranging complete. We're good to go. Now, I can talk to the CMTS, but I don't know what my, I don't have an IP address. I mean, I'm a layer 2 device right now. All I have is a MAC address. I don't know what my service levels are. What's my upload and download speed supposed to be set to? Do I have devices hooked into my Ethernet port, and do they need IP addresses? So all I've done at this point was get the PHY level activity done, and now I'm at layer 2. Next stage from layer 2 is going to be layer 3. We need an IP address, and we need more information. So we go into what's called the provisioning stage. So in the provisioning stage, and again, I'm just going to go past a lot of these slides because they're going to say what I've already said twice probably. But in the provisioning stage, the first thing we're going to do is the modem is now online, but it has not completely finished registering. So if I'm a layer 2 device and I'm in a quote-unquote subnet or domain, right, and I need DHCP, but this guy is actually on another network, can I talk to him as a layer 2 device? Can a MAC address be routed? No. So I have to depend on the CMTS to relay my information if the DHCP server is somewhere else. Yes, but it's called cable helper in the CLI. So I send a DHCP discover. The CMTS relays that actually out to the DHCP server. Now, if the DHCP server is directly connected, the CMTS still wants to be involved. It wants to know what's going on because at the end of the day, there are some security issues here. We have to make sure the correct DHCP server is responding. So, your normal discover, offer, receive the DORA process when it comes with DHCP. So this is going to be a little lame where it's going to sit there, yeah, I hear you, offer acknowledgement. Okay. So our modem now has its IP address, which is called an HFC address. It's normally a 10 or a 192. It's a private network between the cable modem and the CMTS. No computers behind it yet, just the modem itself and the CMTS. So there's actually two separate networks here. When you plug your computer in, you're going over basically a media converter. But the media converter has its own layer 3 connectivity to the CMTS. The cable modem and CMTS have their own IP addressing structure over the HFC interface or the coaxial cable network. And then on top of that, it passes along IP addresses to the customer's devices, your Linksys router or whatever, D-Link, whatever you have, or your computers. Well, in the provisioning process, okay, I just want to skip through some of those slides because we're going to run low on time. But once I get the DHCP address and I actually have an IP address for the cable modem itself, I need something called TOD, or time of day. Anybody ever dealt with the time of day server? Anybody have any idea what that is? Not that timing. There is a frequency timing, and that's a little bit different. The time of day server is kind of funny, but have you ever turned a device on that didn't have a BIOS battery? What date did it give you? Something like 1970? Well, the modem is going to do that too because it doesn't have a BIOS battery or anything else. So it needs a time of day server because anytime it has a log or an error or an issue, it saves it to its own little log server internally. And it's got to have to be able to accurately timestamp that information. So you know, if I had a flap at this point, it's not 1970, it was in 2010. This date, this time, this millisecond. So as you're coming up, part of your provisioning process through RFC 868 is a time of day server. Once you do your time of day server, then you can move on the process. The next process is going to be the TFTP. So this is where the cable modem is requesting its config file from the MSO's TFTP server. This is going to provide the modem information. It could even be providing it a firmware upgrade. But this is going to be the upstream and downstream filters, the caps, quote unquote, that some people want to break. It's also going to provide protection for the customer. You may not want your information and some of your network stuff filtered, but it's probably not a bad idea if well-known port numbers are blocked. And I'm not talking about port 80 because you want to run a web server. I'm talking about known exploit ports. It is possible to put in the modem's config file port filters or a mini access control list into it where it knows that it doesn't need to speak to the 10 network. It knows that it shouldn't go here or shouldn't go there. They're very limited and they're very small and you can only put a couple in there, but 9 times out of 10 those are there actually to protect the customer. There are some service limiting ones you can put in there like port 80 and keep people from sending, actually running an email server. Because we all love spam and we want everybody to have a spam server. But those are some of the things that can be put in the config file. Maximum IP address request is another one. So if your cable company only gives you one IP, they can actually put it in there. So if you ever plugged a computer into a cable modem, you got it online and everything else, then you just switch it over to something else, and you plug it in, it doesn't work. You got to power cycle the thing. Well, because it had a max CP host file in there that said 1. And it already knows the MAC address of the guy that was plugged into it. So you've got to clear it out by resetting it. That's another thing too. So once we actually finish the TFTP process, the last stage is actually option files. We're not going to go into that. Registration request, registration response. Once it finishes its registration, there is one more stage, which is BPI initialization, baseline privacy interface. That's the encryption. So just about every cable company that I know of that is decent sized, at least, is running BPI encryption. It's free. It's part of the spec. You don't have to run it, but it's probably a good idea. So BPI or BPI Plus, depending on what version of Docsis. Baseline privacy interface. So what is that? Well, basically, it's a keying mechanism where I can encrypt the data going down to the customer. I can encrypt that data so only that modem can unencrypt it and read it. So there's no snooping. BPI Plus came in Docsis 1.1, and that actually added an additional field. So BPI, the baseline privacy interface, was set out to protect the customer's privacy. You don't want people sniffing your banking information. You can sniff on a data network. There's ways to do that. It was talked at DEF CON. The one thing that it bring up at DEF CON is everybody uses BPI, so the talk was useless. But there is BPI Plus that came with Docsis 1.1. BPI Plus went beyond just protecting the customer, but then protecting the cable company. So with BPI, it didn't really verify that if the device was cloned or not. So you can't have two devices with the same MAC address in the network because they won't work, right? So with depending on what vendor feature code you have, it'll ignore the second one, or they'll both get knocked offline, depending on the features. But with BPI, you encrypted the data, so nobody's getting the data stolen, but you're not preventing theft of service. BPI Plus, they actually had the manufacturers inject an X509 certificate into the modem's firmware that's actually built into the modem that's signed with the frequency to a root certificate that CA VeriSign approved that's installed in the actual CMTS. So it can verify that's a valid vendor and that's a valid device. Unless you have the vendor's private key to write your own certificates, you're not going to be able to break it. And there's only one way to go around that, and that's called a perfect clone. And you'd have to have physical access to somebody else's modem to do a perfect clone on it. You can't remotely steal it, the information off their modem to replicate it. What's that? No, they should be available. Cable Labs is an open standard, but you may have to be a member to access some of the reading documents. You can, feel free to hit me up later if you want some more information on it. But with Docsis 3.0, it's actually they've changed the whole idea on it, and it's actually 256 AES encryption now, and the rekeying can be set as low as every 5 minutes per device. So it's going to be really hard to break that encryption, and most of us can't afford the equipment and tools to do it. The modem's always going to be sending communications back. The CMTS should always be asking the modem at least every so often, how you doing, how you doing? Great to know you're there. By the way, your levels are fine. Your levels need to be adjusted. Those are normal. That's normal states and maintenance functionality. It's almost like a heartbeat. That's what I just said right there, maintenance. So at least one every 30 seconds it's expecting to see each modem in the plant. One thing I didn't touch. So the VXR I have upstairs, the CMTS I have upstairs, the 7246 VXR, it's capable of supporting easily 5,000 modems off that one device I have. And that's the small one. The one I normally work with my customers on is the Cisco 10012, or it's called 10K. 64,000 cable modems per chassis. But if you're providing any real service, you're going to probably have it around 20,000 to 30,000. So the WAN egress ports and some of the newer stuff at Docsis here, because you're increasing the speed per customer. You went from having gig ports on the actual box to having 10 gig interfaces and multiple 10 gig interfaces. So I'm just about out of time. This is just a customer getting the IP address. Yeah, product overview. I mean, this is a picture of the device I have upstairs. This is the 10K, 10,000 series. It has 8 line cards over here, And these are 5x20s or 20x20s. So 5 downstreams, 20 upstreams, or 20 upstreams, 20 downstreams. And then on top of that, there's the ability to do what's called MCMTS, Modular CMTS, where through the high capacity WAN card slots, I can actually put in what's called a SPA or SIP SPA adapter. And then I can buy these little QAM modulators, and I can add like 24 channels per 1U and just start stacking them and add 24 more downstreams on top of that. So it's gotten more cost effective to be a cable company with these newer technologies. The cost has come down a lot too. Any questions at this time? This is all product literature stuff, so it's not really too deep. Go ahead. No, if the cable company wanted to pull the logs off your modem, which it doesn't contain anything sensitive, it's just signal levels and when it misses a maintenance, they would have to pull that SNMP. So Docsis standard says that even though you have a modem in your house, it's actually the responsibility of the cable company to maintain that device for you. You're not allowed to upgrade the firmware on your own. It only can be done through the Docsis interface. But the cable company is also determining the quality of the network through what it gets back from each of the modems. So 90% of the people don't turn the modems off. That they actually use that to scale to make sure that there's no outages by seeing those online modems because they're talking every 30 seconds anyway. What's that? They're pretty generic. It depends on the vendor, but there's not a lot you can do there that's going to trigger anything. If you're really screwing with your modem, they're already going to see for the most part because your config file, either one, you don't have an X509 private key from the vendor, so you're not going to modify that. Two, if you change your bin file name, they're going to see it because they're talking every 30 seconds, so I know what's going on. If something changes, even beyond signal level, I can easily pull that. Plus, if you tried to clone a device, one, you would have to be on a different CMTS. And I would see where you were, and I would see your signal characteristics, and I could pretty much guess where you're at physically in the real world. And I could overlay my cable plant over a Google Maps and then have a little dot show up, like right at your house. The only time that gets slightly difficult when it's an apartment complex because the houses are so close together. I'm out of time, so thank you. And it's room 226, 6 o'clock or later.